Okay, we're going to finish up talking about infinite limits. Now, infinite limits are basically limits that approach infinity as x approaches a number. So if you look at this function, this vertical line here is the line x equal 2. And notice that as you approach 2 from the left, the graph approaches negative infinity. It decreases without bound. And as you approach 2 from the right, it increases without bound. So the limit of this function as x approaches 2 from the left is negative infinity, and the limit as x approaches 2 from the right is plus infinity. Now remember, those still do not exist because a limit cannot exist unless the limit approaches a real number, and infinity and negative infinity is not a real number. Okay, here's another one. 5 over x minus 2 quantity squared. Notice here, this dotted line here is x equal 2. And notice as you approach 2 from the left, the graph increases without bound. Also, if you approach 2 from the right, the graph increases without bound. So here, the limit from the left would be infinity. The limit from the right would be infinity. You actually could say that this limit itself is infinity. In other words, the two-sided limit actually equals infinity, but since both the left hand and the right hand limit go to infinity, you could say the limit goes to infinity. But again, remember, that's just a special way for a limit not to exist. Here's an example of x over x squared minus 4, and here notice that here's this line here is x equal negative 2, and the vertical line over here is x equal positive 2. And so here notice that for negative 2, as x approaches from the left, it goes to negative infinity, and as x approaches negative 2, let's see. Okay, I did 2 from the left. So as x approaches 2 from the left, it goes to negative infinity, and as x approaches 2 from the right, it goes to plus infinity. Now let's do negative 2. The limit as x goes to negative 2 from the left, it's going to negative infinity, and negative 2 from the right, the graph is going to plus infinity. Here's a trig function, tangent x. I'm just going to focus on pi over 2 and minus pi over 2. This right here represents, this vertical line represents pi over 2, and the other vertical line, I'm not going to label it, but that's negative pi over 2. So for pi over 2, let's see, the one on the bottom, if we approach pi over 2 from the left, that would be coming in from this side. We're going to go to plus infinity, and as we approach pi over 2 from the right, that would be coming in from this side. We would be going down negative infinity. Now negative pi over 2 is right here. So if we approach negative pi over 2 from the left, notice we're going to plus infinity. And if we approach negative pi over 2 from the right, notice we're going to negative infinity. So those are limits that equal infinity. And again, just because I say it equals infinity, it does not mean the limit exists. Now, this is the definition for a function. The definition of the limit of a function that equals infinity as x approaches a number. Basically, for the function to equal infinity as x approaches a number, that means that as x gets closer and closer to that number, like right here, x equal 3 is the number we're talking about. See here, as x gets closer and closer to 3, the functional value can always get higher and higher than any number you choose. So to explain this in simple terms, this m is just some number here. So let's say m was this high. Well, there's an interval here from here to here. If you pick numbers between here and here, you can get values higher than m. So that's true for any level. So if you raised m up, well, there's still numbers between these two numbers that you could get functional values higher than you get here. So basically that's the definition of infinite limits. And then you just kind of have to turn it around for negative infinity. So the limit of a function equals negative infinity. Like for here, the limit as you approach from the left equals negative infinity. Well, pick a number n down here that's a negative number. Well, as long as there's an interval here where you can get a number lower than that value between here and the number 3. So obviously I could pick a number between this point and 3 and I could get a functional value lower. So that means that basically I can get any negative number I want. I can get as low as I want on the negative scale by getting as close to 3 as I need to. Okay, so this one, actually notice this one, as x approaches 3 from the left, it goes to negative infinity, and as x approaches 3 from the right, it goes to plus infinity. Now, the definition of a vertical asymptote is basically exactly what I just showed you. If f of x approaches infinity or negative infinity as x approaches c from the right or the left, then the line x equals c is called a vertical asymptote. So if you go back here, on both of these graphs, the line x equal 3 on both of these are called vertical asymptotes. Up here, the lines x equal negative 2 and x equal 2 are called vertical asymptotes. Here, x equal pi over half and minus pi over half are vertical asymptotes, and so on. Here, x equal 2 is a vertical asymptote, and the same here, x equal 2 is a vertical asymptote. Now, it's pretty easy to find a vertical asymptote. Basically, you're going to have vertical asymptotes generally when you have a rational function. And so what you're looking for is you're looking for any number that makes the denominator 0 but does not also make the numerator 0. So basically, if you have a number that makes the function on bottom 0, as long as it doesn't also make the top number or the top expression 0, then we're going to have a vertical asymptote at that number that makes the denominator 0. You can read my layman's terms there, but it's pretty simple to find vertical asymptotes. So here, x equal 5 makes the denominator 0, and it doesn't make the numerator 0, so x equal 5 is a vertical asymptote. In this rational function, a lot of times you have to factor the denominator. Well, this factors in x minus 4x plus 1. Well, x equal 4 and x equal negative 1 make the denominator 0, so those are the vertical asymptotes. Well, this one I threw a wrinkle at you because the denominator is x minus 3 and x plus 3. Well, you might make a mistake and think that 3 and negative 3 are vertical asymptotes here, but actually only negative 3 is a vertical asymptote. 3 is not a vertical asymptote because if x equals 3 not only makes the denominator 0, but it also makes the numerator 0. So in that case, we would get a whole, but not an asymptote. Okay, so here you can practice on this one. Basically, just find out what makes the denominator 0. Now, so if I want to find wholes and infinite limits, then basically what I've got to do here, if you factor this, the top's going to factor into x plus 4x minus 2, the bottom into x plus 2x minus 2. Since you have a common factor of x minus 2 on the top and bottom, then you're going to get a whole at x equal 2. And since negative 2 makes the denominator 0 but doesn't make the top 0, you're going to get a vertical asymptote at negative 2. For cotangent x, trig functions are difficult because they cycle through several periods. So cotangent x is 1 over tangent x. So if we found out what makes tangent x equal 0, well, tangent x is 0 at any multiple of pi. So any multiple of pi would be a vertical asymptote for cotangent x, because any multiple of pi would make cotangent x, which is 1 over tangent x, have a 0 in the denominator. Now here, sine x over sine x cosine x, well, anything that makes sine x 0 on top is going to make sin x 0 on bottom. So you're going to get a hole at any value that makes sin x 0. And that's going to be basically any multiple of pi, any integer multiple of pi. And then what makes the vertical asymptote is at cosine of x. What makes cosine of x 0? Because if you have cosine of x 0, then the denominator is 0 and the top is not. So anyway, what makes cosine x 0? Let's see, what would make cosine x 0? Okay, actually it would be any multiple of pi over 2, not multiple of pi. So any multiple of pi over 2, you would get a vertical asymptote. So that would be what would make the denominator 0. Actually, it's any multiple of pi plus pi over 2 is what makes the denominator 0 here. So like, let's see, 0 plus pi over 2, or pi plus pi over 2, or 2 pi plus pi over 2, and so forth. That makes the denominator 0. So you get vertical asymptotes at k pi plus pi over 2. Now, to evaluate limits, if you want to know the limit at a vertical asymptote from the left or the right, what I suggest you do, you know that this limit, if as x approaches 1, it's got to go to either plus or minus infinity. So it's got to go to one of those infinity twins. So basically what you can do is just pick a number. This says to the right of 1. So pick numbers to the right of 1 and see what happens as you get closer and closer to 1 from the right. Notice that this is getting to be big positive numbers. So that would be positive infinity. So I would say that this limit is actually positive infinity. Now if you want to evaluate the limit as x approaches 1 from the left, well, then pick numbers close to 1 on the left. And so when I put 0.999 in, I got a large negative number. So the limit as x approaches 1 from the left must be negative infinity. So that's a tactic that you can employ here. Like for instance, on this one, it factors into x over 2 minus x, 2 plus x. And so I know that at 2 and negative 2, I get vertical asymptotes. So I'm going to try to find the limit as x approaches 2 from the left. Well, a number to the left of 2 that's real close to 2 would be 1.999. Well, since I got a large positive number, then I know as I approach 2 from the left, I'm getting plus infinity. And if I pick a number real close to 2 from the right, 2.001, I know I'm going to get, since I got a large negative number, I know this limit's got to be negative infinity. And then actually this one has 2 vertical asymptotes. I found the limits for as x approaches 2 from the left and right. You can actually find the limit as x approaches negative 2 from the left and the right. And this picture should give you a clue of what the answers should be. And so you can evaluate those. And later on in the course, we'll actually talk about limits at infinity, like what happens to a function as x approaches infinity or x approaches negative infinity. And we'll find that sometimes you get horizontal asymptotes, and sometimes you can get what's called slant asymptotes, and then sometimes you'll get neither. So that pretty much covers chapter 1, and the next chapter picks up talking about derivatives.